If you do a free body diagram, you got mg acting downwards. And of course, okay, what we have. It's going to explain 2 kilogram car rolls 40 centimeters down the incline. What's the change in kinetic energy if friction is negligible? First thing you ought to see is change in kinetic energy is F net dot delta S. Make sense? That's where we are. And of course, if you've done the homework for today or even taken a good attempt at it, then you're going to see this. Okay, so you've got your mg force acting straight down, doing a free body diagram. We want to find out what the net force is. Okay, and you're going to have your normal force, which I'll just abbreviate F sub n. And are there any other forces? No. Okay. So you know that if you put your y-axis here and your x-axis here, this force resolves into mg times what? Okay, well, theta is right here. And this side is congruent with this side of this rectangle we get with the projection lines and so forth. You got 0.6 mg there. Down here, you have 0.8 mg. So we can cross out our mg force, and we've got these components. Now we can do this with components and be helpful. I and j components, right? Make sense? Then what's our net force? It's mg sine theta I plus 0j. Why is it 0j? Because we're at equilibrium in the y direction. And when we work this out, mass is 2 kilograms, multiply that by 10 meters per second squared, just to keep the numbers simple. Okay, we get 20 newtons. And we multiply that by the sine theta, which is 0.6, and we get 12 newtons times I. Okay, so now what's delta S? Well, it's 40 centimeters times your I vector. So kinetic energies are F net dot delta S, which is 12 newtons times your I vector multiplied by 0.4 meters times your J vector, which is 4.8 joules. Okay. And that's how you use conservation of energy to determine this without having to get your hands dirty when VF squared equals V naught squared plus 2A delta S. Not that you can't do that. I'd accept that as a correct solution to the quiz because I never asked you to do it using energy consideration. Okay? But what we went over last time shows you how this comes from VF squared equals V naught squared plus 2A delta S. Okay? You can bypass getting your hands dirty on the equations of motion. And this is much simpler because in order to use that, you would still need to do the free body diagram to find out what the net force is. Then you'd have to divide that by the mass to get the acceleration. Then you could get the final velocity squared. Then you could get the final velocity and finally multiply that by 1/2 the mass. Okay? You understand that this is a whole lot more efficient. Plus, it gives you a better conceptual picture. Okay? There's even another picture where you could just take the mg vector downward and do its dot product with your delta S. Okay? So I'm just going to toss that into a little picture here. Now here I'm using just a vertical horizontal coordinate system. Okay, you do negative mgj. And your delta S. Take the dot product of these, and you're going to have the same result that you have here. Now that requires something we'll do later in the week where we develop the idea of potential energy. We'll probably start talking about that today. Now I'll just tell you that this is what you call a conservative force, meaning it conserves energy. Gravity. And the idea is simply, if I lift something up from the floor, say a concrete block, and then release it, the work I did in raising it is equal to the work, equal and opposite to the work gravity does when it drops on my toe. Because I get a little unsteady up here and don't remember to move my feet. And I get complacent because I got steel toe boots. So, you know, run over with a car would hurt. That probably would. Okay. That makes sense? Again, the idea, if the work I would do to raise this thing is equal and opposite to the work done by gravity when I lower it. Okay, because when I raise it, I'm doing work against gravity. Okay, when I lower it, gravity does work on the block. The force that gravity exerts as I raise this is equal and opposite to the force I need in order to raise it, right? In other words, that block weighs about 35 pounds, okay? So I've got to have a 35-pound force up here. That's roughly equal to 160 newtons or something like that, okay? So when I drop it, I've got that 160 Newton force accelerating it downward. So when I raise it, gravity is doing work in this direction. Gravity does negative work. When I drop it, gravity is doing work in this direction. It's positive work. And at every point, it's the same quantity of force, because the gravitational force doesn't care whether I'm raising this or lowering it. Okay? That's an important idea. And let's just oppose that to friction. If I slide that block along the floor in this direction, what's the direction of friction? This way, right? Then if I slide it back, what's the direction of friction? That way. Friction changes direction. So my path, friction is not a path independent force. My path is from here to there and back, friction changes. But gravity, I go from here to here and let it fall back. Gravity hasn't changed a bit. Okay. That's an important idea. So I take the opportunity to mention it right now. We'll develop it more on Thursday. All right. Okay, that's all I want to say about this, but that illustrates what? It illustrates that you got to know what your forces are. Okay, because you don't know about this yet. Okay, turns out that it works, but you got to understand why it works. So if you didn't draw a free body diagram in this, you were lost at the beginning, even though you might have done some relevant stuff in the middle. Okay. If you went to the equations of motion, you bypassed the whole subject of the present chapter, although it shows that you have pretty good understanding of the equations of motion, and that's important. Okay. But we want to learn to bypass them and do things in a simpler manner. Okay. In a manner that's easy to think about. So again, even if you're using the equations of motion, you have to know what the net force is to get the acceleration. And as I said, then you have to use the equation to get the squared velocity. Then you got to take the square root of that and multiply it by 1/2 n. It's a lot more trouble than just figuring out what F net delta S is. Okay, so you want to focus on that. You want to focus on this, which is the work energy theorem. And we expand that a little bit on Thursday. I might mention a little bit of it today. I already kind of did. But we get what's called the idea of potential energy. And I'm going to say it now because you're going to be expected to totally understand it for the rest of your life. The change in the potential energy is equal and opposite to the work done by the conservative force. Okay. So if I lift this thing, the conservative force is doing negative work. Conservative force, gravity is this way, displacement is this way. That gives us negative work. So the change in potential energy is positive. So now I've got all this energy up here. And if I release it, gravity gives it back in the form of a center block that I better keep my toes out from under. Okay? Paradigm example of a conservative force. Friction is a paradigm example of a non-conservative force. Okay, well, I want to expand this a little bit and say, well, yeah, okay, friction isn't really negligible. So how do we analyze this? If the coefficient of friction is, let's say, 0.005. Car has good, let's say 0.02. Okay, because that's typically what your tires have on the road. That dynamics cart there has a much lower coefficient of friction. Okay, probably less than 1%. We can measure it very easily, but we haven't done so. We'll come back to this. And we don't want to do this. I'm going to take just a second to clear this out in case we need it. So again, same cart, same situation. Here's our solution. Look at it again real quickly. I'll move it over here. Now, if you have a coefficient of friction of 0.02 here, what does that do to VF? All right. Well, The only difference we have, if we have this, then friction is no longer negligible. And we have some force of friction. Now, what do you know about frictional forces? Well, if the thing is moving, then the frictional force is just product of coefficient of kinetic friction and the normal force. That's basic. Make sure if you are not totally aware of that, or if you weren't totally aware of that 30 seconds ago, that you become totally aware of it and stay that way, okay? It's a lot of stuff here to sort out. So if you didn't get it, there's no huge shame in it. But if you did, which seems like about half and half in the class, okay? Or some of the half is about half of the half. You got, you know, force of friction is 0.02 times your normal force. Okay. What's your normal force? Well, it's equal opposite to component of gravitational force here. So here's your mg cosine theta. And I never did write that as negative mg cosine theta, but that's where the point A came from, right? Yeah, yeah, right here. You got this triangle. Here's your theta. Here's mg sine theta. Here's mg cosine theta because this is mg. Make sure you're really, really clear on every detail of that. Because I think if you're having problems with the homework and so forth, a large part of it goes back to having not quite mastered through body diagrams, at least in the most basic situations. Okay, pendulum, mass on an incline, chain. Okay. And then you got the centrifugal force and all that stuff on the rotating beam, which has a little more content, it's a little more complicated. But if you understand these, that becomes accessible, okay? So, here you got it. So now what's your net force? You got your mg sine theta here, and your negative UK mg cosine theta I, and you put the numbers in. And you got that 2 kilograms. Okay, so that's going to be 12 newtons minus 0.02 times 16 newtons times I. And the 16 newtons is just your mg cosine theta. This is minus because look at your arrows. One's in the positive x direction, one's in the negative x direction. Okay. And just think about what's going on. The thing's trying to get down the incline, being accelerated by the component of the gravitational force in the x direction. with friction opposing it. So obviously, these two are going to have opposite signs. So this is in the direction of motion, and this is opposite the direction of motion. Make sure you understand all those words. Okay, well, that's going to be 0.32 newtons. That's going to be 11.68 newtons times I. You know, when I wrote this down, I've written an I just want to write a J. Obviously, this 0.4 newtons was times the I vector because it's in this direction. It's in the X direction. I just wrote a J because my hand wanted to write a J after it wrote an I. And has no sense at all. And sometimes the brain misses it. Okay. So what's that going to be? It's going to be 48 joules minus 0.32 times 0.4, which is 0.142. 128. So it's 1.128 joules less, and that's going to be doesn't seem right. Seems a little low. Not a whole lot less, but that's enough friction that it bothers me a little bit. So work it out and get the numbers. Okay. I would have thought the friction would have done a little more than that. I don't want to take the time to last time to figure that out, but that is 0.32. 0.32 times 0.4 is 1.28. Take off 0.128 from that.
An extra decimal.
It looks like somebody's got a. Okay, somebody with a calculator telling me that I was right. Intuitively, that ought to be 4.6. Also, when I looked at the 4.8, I didn't see the decimal and I didn't think through the calculation, but obviously, if I multiply 11 by 0.4, I'm not going to get 40 something. I'm going to get 4 point something, okay? So just 872 was right. So I did something right, but that's, that 872 ain't all that important, you know. Make that a 0.69 or even a 0.7, okay? But it does decrease the kinetic energy from about 4.8 to 4.7 joules. Okay. And that feels a little better than decreasing it by only 1/10 of a joule. So. Which it feels better to me. I don't know if it feels good. Out there, probably nothing much. But there it is. Okay. All right. You're gonna love this, but I'm gonna add another course. Okay. So let's do the same thing. Here's your card. 2 kilograms. LS is 40 centimeters down the incline. But I'm gonna include a horizontal force. I'll leave the frictional force in there since we've already worked it out. And let this force be I'll call that FF for force applied. And let's let that be 3 newtons. In the horizontal direction. So what does that do? First of all, what's it do to your free body diagram? We're gonna have to redraw the free body diagram since there's no place over here where I can draw that force without crossing out something. Okay. So draw the free body diagram and show on the free body diagram what you're gonna do to get the net force in the I direction. And you're gonna also have to analyze the J direction. Okay, everybody's pretty much got a good free body diagram, but I've seen diagrams that look like this. Okay. You want this force, you want all the forces to act on this point, okay? So you really want to draw it like this. Okay, you want to draw that applied force with the initial point on the dot. If you draw it here, you're not going to be able to do what I'm about to do. So here you go. Here's your x-axis. Here's your y-axis. Any force that's not along the axis needs to be resolved. So your weight is going to have components here and here. And your applied force is also going to have components here and here. That makes sense? So if you draw the arrows in the right direction, I don't care if one of them is way too big. I mean, you try to want to get them in, you know, your frictional force is a whole lot less than any of these other forces. Matter of fact, it would be a lot smaller than what I've drawn here. Okay, so if you drew your frictional force all the way out to here, it's okay as long as you represent its components. So what I'm doing now is I'm kind of crossing out the applied force. And I've got these forces. I should have drawn a bigger diagram so I can label them. And most of you should have drawn a bigger diagram. Okay, because there's a lot of stuff going on here and you're going to want to label stuff. Okay, now in my case, I've got the same labeling I had over there. But the additional thing is this applied force. So this applied force makes a 30-degree angle with the x-axis, right? Or 37-degree angle, which means that this is going to be negative 0.6, well, would be negative 0.8 I plus 0.6 J times 3 newtons. Now notice I wrote this, which is a unit vector in the direction of the applied force. And I multiplied that unit vector times the magnitude of the applied force. Okay? Because that can be a very convenient thing to do. If you want to do negative 0.8 times 3 newtons plus 0.6 times 3 newtons, well, negative 0.8 times 3 newtons times I and 0.6 times 3 newtons times J, you can do that. It's going to come out the same either way. So that's negative 2.4 newtons times the I vector. Plus 1.8 newtons times the J vector. Now, all the other forces and components are identical, well, to what I have here, because I'd already accounted for all the other forces except the applied force, right? So we can say debating about how to do this. This force and this force are both equal and opposite to the net force. Okay. And these things all add up to 0. So the net force is now 1.8 newtons plus the 12 newtons and 16 newtons we have here. And why do we even bother with normal force, since all the forces that we are interested in are in the X direction? Well, because we've changed the normal force, which is going to change the frictional force. That view came out really bad, but there it is. Okay, and that's going to be 0.276 newtons. And some of those significant figures aren't really significant, okay, in the whole picture, but we'll keep it for now. So we have this force.
That's how it always.
Those guys weren't that bad. When everybody comes out from that big announcement they're making, cheering and hollering and stuff, we won't be able to hear anything. I don't know what the big announcement is. I'm really kind of interested to hear what it is. And we'll find out later this afternoon, I guess. Okay, so anyhow, we've got this. So we can say that the force of friction with an arrow over it is negative 0.276 newtons times the I vector. And now F net is your 16 newtons, that's 12 newtons. Minus 0.276 newtons times I, which equals 11.724 newtons times I. Again, that's a ridiculous number of significant figures. I'd probably round that to 11.7. But we haven't specified just how accurately these things might be measured. I will tell you though that friction is never reliable to that many significant figures. Okay. So we could just call that maybe 0.3 newtons and get an 11.7 here. Still, pretending that we can know friction that accurately and measure everything else that accurately. Here we got it. Okay. Then in this dot product, I dot I is 1. Your basic premises, but you know, I assume that everybody understands that. Okay. So this is going to be what? Let's get the decimal in the right place. Okay. That's going to be 4.58 joules approximately. And that's not enough. So what's going on? Oh, heck, I left something out. I left out my component of the applied force. And I'm so focused on how the frictional force changes. Now, there's where my intuition comes in. I know that that 3 Newton force is going to significantly reduce the kinetic energy. If that 3 Newtons was in the direction up the incline, it would reduce it by 1.2 Newtons, all the way down to around 3.6, 3.5 something, even 3.4 something. Okay, so I've got to go back and fix what I did. And that was I really made that mistake. I was just trying to illustrate something, but let's try to make the best of it. And it's going to be plus this component of the applied force, which is 2.4 newtons. And it's minus 2.4 newtons. So this is mgx. This is mu times the normal force times J. And this is the X component of the applied force. And all those get added up to give you the net force in the I direction. The net force in the J direction is still 0 because this thing isn't coming off or breaking down through the incline. We have no motion with respect to the y-axis, and we got a question. Up, you know, the arrow is right over the pause button. Okay, we had a little confusion there about what that 1.8 newtons means, which caused me to go back and look at this and explain where it came from. And this had a plus sign on it, didn't it? But of course, it's in the negative J direction, and I just put down a plus carelessly. So keep your bookkeeping straight like I don't. But then this sum, you could write out. This is going to be negative 1.8 newtons J. This is going to be negative 16 newtons times J. I'm sorry, this is going to be negative 16 newtons times J. This is what's going to be the negative 1.8 newtons. And the normal force then is going to be equal and opposite to what you get from these. And these are both negative. You put them together. You need to write that out in clear mathematical terms. Okay, I skipped that step because of time and because I want you to fill that in, okay? So you should be filling these things in and making sure you see how it is, because again, by writing out exactly what's going on, you pull it out of your memory, out of your subconscious, out of whatever you're doing, and you focus on it, and that's how you learn it, okay? That's how you learn it in such a way as to retain it. Okay, so there we have it anyhow. So I think we've answered that question and also corrected something I wrote down carelessly. All this, I believe, holds if I've done my arithmetic correctly. And now we have not 11.724. We got to subtract 2.4 from that, which gives us 9.324, I believe. And that's number reduced times I. And we take 0.4 times that and we get 3.6, 3.728. Little question mark on that number, but I think 3.7. About right, except that can't be right. Okay, if I subtract 2 from 11, I get 9, and subtract 0.4 from this, I get 0.324, 2.728. Well, seems like it's the right ballpark. Something I'm looking at doesn't feel right, so I'd want to double check that, okay? But the numbers just follow from the entire analysis, and we can get that whole idea. Okay. There's a problem very much like the one I'm going to put up here. And I'm not sure whether I signed it or not. I think I would tend to want to sign it, but it does require some integration, which is not going to be a problem for anybody. But we want to kind of get used to that a little bit, whether I could legally put it on a test at this point or not. It's going to be all over the place in the spring, okay? So we want to get our feet wet. So let's say we have five xi minus 3y squared j. That's our net force. Okay. Your belt ash goes from 1 meter, 2 meter to 4 meters, 3 meters. Okay. You know, I thought I wanted to do this, but we've got 5 minutes left. I might want to defer this to next time. I'm going to defer things. Not what I think about it. You go from some point here to some point here, and you got this force that depends on where you are. It's a variable force. actually gets us into line integral, which is beyond anything we can ask you to do through the whole here. Okay. If you've been through multivariable calculus, of course, you know how to do that. But I think only one of you's been through it. So we're not going to do that. Okay, let's just do. I'll leave that as a question because I've only got 4 minutes left now. Okay, I've got a crate. Sliding along the level floor. Moving at 7 meters per second, which is pretty fast. Okay. That's faster than probably anybody in here can run. Okay, way faster than I can run. Coefficient of kinetic friction is 0.3. So it's actually a pretty smooth surface. This one probably has a pretty smooth surface on the bottom, because that's not a very high coefficient of friction. How far does that go in order to stop? Well, I'm not going to get anything out of it here because now we've only got 2 minutes. But kinetic energy is 1/2 mv squared. That means half of 490 joules, which is 245. Kinetic energy equals 0. So F that dot delta S equals 0 joules minus 245 joules, which is of course a change in kinetic energy. Now, if you think the change in kinetic energy is plus 245 joules, you're going to find that it never stops. Okay, so you want to be sure you have the signs right on this. You subtract where it is from where it's going to be. Where it's going to be from what minus where it is. So F net delta S equals 100 newtons times 3. And let's say negative this times your I measure, where your I measure is in this direction. So that's negative 30 newtons times I. Delta S equals delta S of those. And I'm going to write big times I. So you set this up as F net dot delta S equals change in kinetic energy. That's negative 30 newtons times I dot delta S times I equals negative 245 joule. So this is negative 30 newtons times delta S is negative 245 joules. Delta S equals negative 245 joules over 30 newtons equals 8.16 repeating 56 repeating 56 meters. And we never have to get our hands dirty with VF squared and VF squared to the delta S. Okay. So digest that. And we took, oh gee, according to this, we're early, according to that, we're a minute late. Close enough.